What if I told you that a simple spark, just a tiny flash of light hitting a piece of metal, was the clue that completely unraveled our entire understanding of reality? It sounds like something out of a movie, but that's exactly what happened. So let's dive into this fascinating mystery, the one that kicked off the quantum revolution. So our story kicks off way back in 1887. Physicists were noticing something kind of weird. When you shine a beam of light on certain metals, we're talking things like potassium or cesium, they almost magically start spitting out a stream of electrons, which creates an electric current. It was a really reliable effect, but nobody could quite figure out why it worked the way it did. And this phenomenon got a name, of course, the photoelectric effect. Let's just quickly break down what you're seeing on this slide. You've got the incident light beam, that's just the light you're shining on the metal. Then there's the metal surface, which is where all the electrons are hanging out. And when that light hits, boom, out pop the ejected electrons. Seems pretty straightforward, right? Well, the devil was definitely in the details. You see, this whole thing wasn't random at all. It was governed by a set of really rigid, totally unexplainable rules that just seemed to defy all the physics people knew at the time. And these rules, they were the clues to a much, much deeper secret about what light actually is. So here they are, the three big mysteries that had physicists scratching their heads. First, the effect was instantaneous. The moment the light hit, electrons came out. Second, the quantity of electrons depended on the light's intensity or brightness. And third, the energy of those electrons depended on the light's frequency, which is basically its color. Now let's really zoom in on those last two because that's where things get really, really strange. Okay, rule number 2. Common sense, right? Your gut feeling would tell you that a brighter, more intense light is just, well, more powerful. So you'd totally expect it to knock out electrons with more energy, making them fly off way faster. But that's not what happened. A brighter light just knocked out more electrons. Each individual electron had the exact same energy as before. The quantity went up, but not the quality, not the power. And this brings us to the rule that broke everyone's brain. For each metal, there was a specific threshold frequency. If you used light that was below that frequency, let's say you use red light on potassium, absolutely nothing would happen. You could make that red light blindingly intense, 1,000,000 times brighter, and not a single electron would even budge. But then, if you hit it with even a super dim light of a higher frequency, like yellow or blue, electrons would pop out instantly. It was the color of the light, not how bright it was, that held all the power. So, of course, physicists turned to the established laws of the day, to the grand theory of classical physics. I mean, this was the theory that treated light as a continuous wave, and it explained so much about the world. Surely, it could explain this little spark. The classical wave theory made a really clear prediction. It said the energy of a wave is all about its amplitude, which for light just means its brightness. So a very bright light, it doesn't matter what color, should be carrying a ton of energy. The idea was, if you just blasted a metal with it for long enough, an electron should be able to slowly soak up that energy and eventually break free. But reality? Well, reality had other plans. And this slide right here is the smoking gun. It just perfectly illustrates the breakdown. Over on the left, you've got this super intense red light. Its frequency is too low for potassium. Now, according to the old theory, its sheer power should eventually free an electron. But what was the result? Zero. Nothing. Not a single electron. But then on the right, you have a faint yellow light, which has a higher frequency, and it works instantly. The theory wasn't just a little bit off. It was completely, undeniably wrong. And this was the question that stumped everybody. I mean, if the centuries-old understanding of light as this gentle, continuous wave was just wrong, then what in the world was it? The stage was perfectly set for a brand new idea. And the detective who finally cracked this case? Well, it was a young patent clerk named Albert Einstein. In 1905, he proposed a solution so radical, so out there, it would change physics forever. Einstein's idea was breathtakingly simple. He said, light is not a wave, it's a stream of tiny individual energy packets. He called these packets photons. And here's the absolute key. The energy of a single photon has nothing to do with the light's brightness. It depends only on its frequency. A photon of blue light has more energy than a photon of yellow light, which has more energy than a photon of red light, period. And let's be really clear about how huge this was. We all know Einstein for relativity, E equals mc squared, all that, but it was for this exact explanation, for figuring out the secret of the photoelectric effect, that he was awarded the Nobel Prize. It was that revolutionary. So, how did this new photon idea explain everything so perfectly? Well, it wasn't just a cool concept. It was backed by some really elegant math that described the whole interaction precisely. It created a perfect energy budget. Okay, the first piece of the puzzle is something called the work function. The best way to think about it is like this. An electron is kind of stuck inside the metal. To get it out, you have to pay an energy toll. The incoming photon is the money. If the photon has enough energy to pay that toll, the electron is freed. If it doesn't have enough, well, nothing happens. That toll is the work function. And what's really cool is that every single metal has its own unique work function, its own specific price to get an electron out. You can see it right here in this table. Potassium has a pretty low toll, right, at 2.25 electron volts. That's why it's so sensitive to visible light. But look at copper. It has a much higher toll of 4.8. You need a much more energetic photon, like one from ultraviolet light, to get an electron out of copper. And this all comes together in one beautiful, simple equation. The total energy of the incoming photon gets split into two parts. First, a chunk of that energy is used to pay the work function. That's the toll we just talked about, the price of admission to get out of the metal. Any leftover energy, the change, becomes the kinetic energy of the electron, which is what makes it move. It's a perfect, balanced energy budget. Now, to give you a sense of just how wild the scale is here, let's look at a regular old 100-watt light bulb. That bulb is putting out 100 joules of energy every single second. Okay, now the energy of one single photon of yellow light is incredibly, incredibly small, about 3.6 times 10 to the power of negative 19 joules. It's tiny. So when you divide the bulb's total energy per second by that tiny amount, you get the number of photons. And the result? It's over 200 quintillion photons every single second. Light isn't some gentle wave. It's an unbelievable storm of these tiny particles. And this perfectly explains that old mystery, rule number 2. Turning up the brightness doesn't make each photon stronger or more powerful. It just means you're sending out more of them. As this slide shows so well, a low-intensity beam is like a trickle of photons, and it ejects a few electrons. A high-intensity beam is a flood of photons, and it ejects a whole bunch of electrons. Mystery solved. Einstein's solution, though, did way more than just explain a weird effect. It shattered the classical view of the universe. It forced physicists to accept a strange and wonderful, and frankly bizarre, new reality. This led to what is now a cornerstone of all modern physics, wave-particle duality. The evidence was just undeniable. In some experiments, light behaves exactly like a wave. But in the photoelectric effect, it behaves exactly like a stream of particles. It wasn't one or the other. Light was somehow, bizarrely, both at the same time. So, what's the big takeaway from all this? Well, the photoelectric effect proved that light has this split personality. It's both a wave and a particle. It showed us that energy, down at the atomic level, is quantized. It comes in these discrete packets, and that energy transfer can be instantaneous. This dual behavior wasn't some weird fluke. It's a fundamental rule of how our universe actually works. So, from a simple little spark on a piece of metal, we discovered that reality is far stranger and way more fascinating than we ever imagined. It proved that even something as familiar as light can have a secret identity. And that kind of leaves us with a final thought, right? What other profound secrets are just hiding in plain sight, waiting for the right person to ask the right question?